You're going to have assignments where you're going to have to make motion diagrams to represent the motion of an object graphically and semi-quantitatively. So what that means is that there are going to be dots representing the position of an object at different times. The position of the object is represented on these axes here. So the horizontal axis could represent the x position in, say, meters or some other distance type unit. And the vertical could represent the y position, also in meters, but we'll see that maybe sometimes there's another way to interpret it. So when you're thinking about the different dots that we're going to place here, you should think of sort of like a strobe light. And I'll put a link to another video of exactly that scenario with a strobe light and a ball falling. So you can see that what we're looking at is the dots at evenly spaced intervals in time. So what we're going to do is we're going to think of two different scenarios and make the motion diagram for those two different scenarios. In the first one, we're going to have a car that is starting off at a pretty fast speed, and then it's going to slow down and stop. And the amount that it's slowing down, its acceleration, is going to be a constant amount. I did say acceleration. You might be thinking of acceleration meaning only speeding up, but you'll see in your physics class that's not how the word acceleration is used in physics. It can mean any change of speed and direction. So what we're going to do is we have these arrows and dots that we're going to use here. You can press Control D on a Windows computer. I think it's probably Command D on a Macintosh, but I don't really know. To place the dots to represent the position of the car at different times. And this is going to be semi-quantitative, so we're not going to actually worry about what the numbers mean in this case, but we are going to pay attention to the grid. So this is where we're going to start. We could have picked any position along here, but why not pick the origin? And at the next interval of time, we're going to put it some later in position. And so, so far we're thinking of the car moving to the right. And then since it's slowing down, the next interval needs to be a smaller distance, right? So in the first interval of time, let's say that it's 10 seconds, right? So in the first 10 seconds, you'd think that the car would move pretty far, but since the car is slowing down in the next 10 seconds, it wouldn't make it as far, right? So if it moved 300 meters in the first 10 seconds, maybe it only moves 200 meters in the next 10 seconds, maybe it only moves 10 meters in the next 10 seconds, or sorry, 100 meters in the next 10 seconds. So these are our position markers. The next thing that we're going to want to place are velocity or displacement arrows. You can kind of think of them either way. What they literally are displacement arrows, so they are changes in position. But because velocity is a displacement divided by a change in time, a duration, they're also telling us what the velocity is, relatively speaking. It's a little bit tricky to get this to click right in the center. So I'm going to go, what we'd really love is if this went from center to center, but Google's being a little mean with me right now. Oh, I know what we can do. We can change it after. There we go. So we have a velocity arrow from center to center. So that's telling us not only how far we went during that interval time, it's also telling us which direction, right? Because if we only had the dots, we'd have no idea whether this was a car slowing down going to the right or a car speeding up going to the left. So these velocity vectors are going to make very clear which one is happening here. And we're just going to do our best trying to get these vectors to look correct. So the trick that I'm doing here is, since it doesn't really want me to draw from center to center, I'm drawing it from edge to edge and then moving it center to center. Okay, so we can see that the magnitude of the velocity vector is getting smaller each time, and that supports our notion that the speed is decreasing. Now, we're going to draw acceleration arrows for each one. And the acceleration arrow is going to tell us whether the acceleration is pointing the same way or the opposite way, or if there's just no acceleration at all. So let's duplicate our acceleration arrow. And in order to find this, what we're going to do is we're going to think of this arrow, the one that we started with, as the initial, and we're going to think of this arrow as the final. It's not the most final, but it's the final one we're considering right now. And we're going to think, what do I have to do to the initial vector to get to this final vector? What do I have to add to it? Well, our acceleration vector has to point that way to add to our initial velocity vector to end up to our final velocity vector. So we have to have an acceleration pointing to the left. Let's look at these two velocity vectors. So now we're going to think of this as the initial velocity vector when we're at this point, and this as the final velocity vector when at this point. So when we're looking at acceleration, we're looking before and after a given dot. What do we need to add to the initial to end up at this final? Well, it turns out to be that same sort of one grid space of acceleration. So we can put our velocity vectors back, and we always put the acceleration vector over the dot. Now, because there's no velocity before the first dot and there's no velocity after the last dot, we're not going to put acceleration vectors on those. So that is what a car slowing down while traveling to the right is going to look like. So let's make a copy of this. It's not really necessary to make a copy of that, but we are going to change the scenario a little bit, and we're going to say that this car is actually going to turn around now and speed up back the way it came. So what does that look like? Well, the first thing that happens is that after the point where it's come all the way to the end, it's going to start coming back the other way. But for just a moment, it's going to sit still, right? Now, how do you want to do that? You could put side-to-side dots, or you could just have that one dot there. There's some wiggle room, but I am not going to put side-by-side dots for that one moment where it's perfectly still. Instead, we're going to start talking about moving back the way it came. So how do we represent that? Well, it's starting here, and it's going to be moving to the left. But it's going to initially be moving pretty slowly. And it might, if we further assume that it has the same amount of acceleration the entire time, which I would have to state if I were giving you the physical scenario, the amount of distance that it covers in that short time interval is going to be the same amount of distance that it covered during that last time interval when it was slowing down. Same sort of thing during that next time interval, and the same sort of thing during the next time interval. The main difference now, of course, is that it's going this way. Now, you can be however picky you want with actually drawing this. When I have moved this downward, we're not saying that the object physically moved to the side, right? We're just saying, I don't want to overlap my drawings. So you might want to make some sort of curvy line, indicating that it's going off to the side. But that's not particularly important to me. We basically know what we're saying here. We're saying that that object is the same position down here, and it's now moving to the left. And we can continue navigating this motion, and it's going to keep on speeding up as it moves to the left. And I basically already said that we are assuming the same acceleration. So we will just copy our acceleration vectors down here. And now we can see that we have slowing down to the right. It's stopping for a moment, and then it's speeding up to the left.